Dear students, I welcome you to the online lecture series of our course Waves and Oscillation. Before the break, we have already taken 6 lectures in this course. In this 7th lecture, I will refresh your memories before proceed with the onward course. Okay. Up till now, in this course, we have discussed the simple harmonic motion and its mathematical description, the energy in simple harmonic motion, and then we have discussed some of the angular forms of the harmonic oscillator. And lastly, we have reviewed the uniform circular motion and obtained simple harmonic-like solution. In this presentation, I will review these topics. Simple harmonic motion is a kind of periodic motion where restoring force is proportional to the displacement. For instance, we have a harmonic oscillator in the form of a mass attached to the spring. If we displace it here from the equilibrium position, it will set into motion such that the displacement vector periodically changes. Xm represents the maximum displacement from the equilibrium point, and this x of t changes periodically. The velocity and acceleration vectors can be obtained by differentiating x of t. This factor is equal to x of t, and hence we can write it as acceleration is proportional to the instantaneous displacement. The phase constant phi tracks the state of motion during the dynamics. Generally, we refer these three equations as a motion parameter in mechanics, and they may change if we change the configuration of the system. In order to obtain the equation of motion for objects performing simple harmonic motion, we can write F is equal to ma. Substituting the value of a from the previous slide, defining this constant k here and replacing this factor xm cos of omega t plus phi by x of t, we can obtain the linear restoring force. Now, actually, this force is responsible for the motion of the system shown here. For a one-dimensional system, let's say this is the x direction, then one can write this mx double dot equal to minus kx. That is, the motion is due to the restoring force minus kx. Remember, this is the ideal situation where we do not have any resistive force on offer to the motion. Hence, we have the simplified version of the equation of motion for harmonic oscillator. Now, the solution of this equation give us the same x of t equal to xm cos of omega t plus phi. This is the solution of the differential equation. On the last slide, we have the force equation of an ideal linear harmonic oscillator where F is equal to minus kx is responsible for the motion. The associated potential energy can be obtained from this force equation as F is equal to minus curly u by curly x. For one dimensional, we can write it as du by dx. That is, by integrating this force, we can obtain the potential energy and similarly the kinetic energy. The total energy is the sum of these two energies. Adding these two equations, one can get this energy, the total energy, as half kxm square. Now, during the motion, as time changes, the energy shifts between the two types such that the total energy remains constant. We have already solved a problem on this particular situation. In the angular form of simple harmonic oscillator, first we have this torsion pendulum, in which we have a circular disc suspended from this fixed point with the help of this suspension string, such that the disc rotates in horizontal plane. Let's say the angular displacement is theta. The equation of motion now becomes tau is equal to minus kappa theta, which is similar to F is equal to ma, where this kappa depends on the properties of the suspension wire. By properties, I mean the length, diameter, and the material from which the suspension wire is made. This I alpha represents the restoring torque, where this alpha is the angular acceleration and can be write as theta double dot, theta being the angular displacement. The equation of motion is similar to the one we obtained for the spring mass system, x double dot plus k over m x equal 0. Another system where it is easy to work with polar coordinates is simple pendulum, in which we have a mass attached to this massless string of length L from this point. The equation of motion is tau equals minus L f of g sine theta. Generally, we know that tau is equal to r cross f. Since this is a restoring torque, so there is the negative sign. In our case, instead of r, we have L being the length of the pendulum. This f sine theta is the effective component of the force which produces this restoring torque. So, if we see here from this figure, at this point, this Fg points downward, making an angle theta, such that we have these components Fg sine theta and Fg cos theta. The effective component of the force which is responsible for the torque is Fg sine of theta. So this tau can be written as I alpha, where I being the moment of inertia about the pivot point and alpha being the angular acceleration. Alpha can be written as theta double dot. So this equation becomes theta double dot plus mg times L over I sine theta equal to 0. For small theta approximation, this equation is written as theta double dot plus the factor which is omega squared times theta. Since for small theta, sine theta is very small, so it's equal to theta. So if we write this I equals to I m L square, generally the moment of inertia about the pivot is mr square, but in our case r instead of r we have L, so we can write this I equal to ml square and obtain the angular frequency for the simple pendulum as g over L. Now we will see the similarities among an object performing uniform circular motion and the equation for simple harmonic oscillator. Let's we have an object moving along this circular path at any time t. Let assume that it is at point p prime. such that the projection is P along the diameter. This point this point P executes simple harmonic motion. Now, in order to obtain the relevant equation, we have this vector xm making an angle omega t plus phi at the origin. The x component of this vector xm is x of t. Since this x of t varies with time, this is like a rectangular component. Once we have a force F, then the x component f of x is f cos theta. So here this x component x of t is the vector times cos of the angle. So we have x of t equal to xm cos of omega t plus phi, which is the same as we obtained for the simple harmonic oscillator. Now, for the velocity expression, if we assume this figure at point P prime, the velocity is omega times xm. Generally, for the uniform circular motion, we know that V is equal to r omega, r being the radius. So here we have xm being the radius. So we have this omega xm. Again, the x component of the velocity or the radial component is x of t, which is the vector times sine theta. But here we have omega t plus phi. And likewise, we can have the acceleration being this acceleration, and its value is omega square xm. And the x component is again minus omega square xm cos of omega t plus phi. So we can see that the three equations for the x, v, and a are similar to the one we obtained for the simple harmonic motion. After this review, in the next video, I will present the damped harmonic oscillator. Thank you very much.